Hello everyone. So hope you are doing very well. Today we are going to study about the theory part 2 of coordination compounds. And today we are going to cover the NCRT section 5.3. So let's begin our today's topic, that is NCRT chapter 5 coordination compounds theory part 2 section 5.3. This is disclaimer. So let's see the objective of today's lecture. After attending this lecture, you will be able to learn the rules of nomenclature of the coordination compounds and write the formulas and names of mononuclear coordination compounds. So today we are going to cover the rules of nomenclature of coordination compounds and the formulas and names using the nomenclature for the mononuclear coordination compounds. The topics we are going to cover today according to the NCRT are: first is the section 5.3, that is nomenclature of coordination compounds. In this, the first subsection we are going to cover is formulas of mononuclear coordination entity, which is 5.3.1. In this, we will talk about the rules for writing the formula of any coordination compound. Then we will see the section 5.3.2, including the naming of the mononuclear coordination compounds. In this, we will see the rules for naming of the coordination compounds. Then we will see some examples of nomenclature of the coordination compounds. And lastly, we will going to have the examples marked as 5.2. So let's begin. First of all, let's begin with our first section 5.3, that is nomenclature of coordination compounds. So in the nomenclature, what is nomenclature? Nomenclature is very important in the coordination chemistry to describe the formulas of the compounds formed by the coordination complexes, to give each compound a unique and unambiguous name. Okay, so because we are studying about the coordinate complexes, that means to each and every complex to give a unique and unambiguous name on basis of some rules. That is very important. So we study the nomenclature to do that. Third point is we use the nomenclature to differentiate between the isomers. So if any two molecules are having same formulas, then how they structurally are different. Okay, then also nomenclature point comes. How using nomenclature of those two compounds, of those two structures, you can differentiate between the isomers. The formulas and names adopted for the coordination entities are based on the recommendations of IUPAC. So this is not like we do it by ourselves. Basically, the formulas and the name that are going to be adapted by the coordination entities. Remember, we have studied the coordination entities about it in the previous part. So the names or the formulas that we are going to assign to the coordination entities, they are particularly based on the recommendation of IUPAC. IUPAC is basically the International Union of Pure and Applied Chemistry, a union organization which is going to it is like the head of the chemistry, which is play a very important role in the nomenclature or naming or formulating for the different compounds. So let's begin the section 5.3.1 covering the formulas of mononuclear coordination entity. So let's first see the rules for writing the formula of any complex compound. A chemical formula is a coincidence way to show what a compound is made up of. Okay, so basically, if you have a compound and you have the compound's formula, so using that chemical formula for a particular compound, you can, in a short way, show that what compound is made up of. Mononuclear coordination entities contain a single central metal atom because, as I said, mononuclear, one. Okay, mono means one. So mononuclear coordination entities are those that contains a single central metal atom. Only one central metal atom is present in the coordination entities which are mononuclear. The rules that are applied while writing the formulas are: first is the central atom is listed first. Remember, we have studied the central atom definition. In the complex compound, in the coordination entity, the core of the coordination entity or coordination sphere is considered as the central atom or ion. When you are writing the formula of any coordination compound, first thing is that you have to uh, write the central atom first. Okay, you have to write the central atom first. Second rule is that the ligands are listed in alphabetical order after the central atom. Now, first is the name of the central atom that is going to be okay, symbol of the central atom that is going to be written in the formula. Then, after that, after writing the central atom symbol, ligands you have to put in the alphabetical order. Polydentate ligands are also listed alphabetically. So we have been studied about the ligands. Ligands are basically the number of compounds, the number of molecules or atoms that are going to arrange themselves around the central metal by bonding with the central metal by forming coordination covalent bond, right? In that, polydentate ligands are those in which more than two donor atoms are present. Okay, so we have seen the rules that firstly you have to write the symbol for the central atom while writing the formula of the coordination compound. Second thing you have to remember is after writing the central atom or ion symbol, you have to write the ligands in the alphabetical order. Now, if there is a polydentate ligand, they are also going to listed alphabetically. Now, in case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. Okay, so if there is a ligand which is abbreviated, then that abbreviation first letter is going to decide the position of the ligand in the formula. So basically, we have to follow the alphabetical order. For example, let's say En. En is for ethylene diamine, right? Now, this would be placed before the oxalate OX. Okay, so these are ligands basically. They are polydentate ligand, ethylene diamine and the oxalate. Uh, they both are polydentate ligands. And what we are saying that if they are abbreviated. So ethylene diamine is written as En and oxalate is written as OX. Now we have to decide the position of these ligands. So that will be decided by the first letter of this abbreviation. So first letter of this abbreviation is E. Similarly, the first letter of oxalate is O. So E comes before O in the alphabetic order, right? So we place, if both the ligand are present in the same chemical compound, the same complex compound, then this ethylene diamine would be placed before the oxalate. The formula for the entire coordination entity is enclosed in the square brackets. Fourth rule while writing the formula is that the formula you have to write for the entire coordination entity, then you have to pack it in a or enclosed it in a square brackets. When the ligands are polyatomic, their formulas or their abbreviations of ligands are enclosed in parentheses. Okay, so when the ligands are polyatomic, that means it has different atoms. For example, ammonia. Ammonia is written as NH3. So it is polyatomic, nitrogen and 3 hydrogen is present. So in that case of ligands, while writing the formulas or abbreviations of the ligands if present, then we enclose them in the parenthesis, in the like brackets. Okay. Okay. The fifth rule is going to be that there should be no space between the ligands and the metal within the coordination sphere. The coordination sphere corresponding to that square bracket and whatever is present inside that square bracket. Okay. Basically, in the square bracket, we contains the coordination entity including central atom or ion and ligands. Okay, the counter and will be outside of the square bracket, and this whole coordination entity when enclosed in the square bracket, that is called as coordination sphere. What we are saying that in the coordination sphere there should be no space between the ligands and the metal. Only two things can be present inside the coordination sphere, the ligands and the metal. And also we are saying the fifth rule as, while writing the formula, that between those ligand and metal only there should be no space while writing the formula of the coordination compound. The sixth rule says that for a charged coordination entity, the charge or the number then sign is written as a superscript outside the bracket. Okay. So if our coordination entity is charged, if any coordination entity is charged, that charge or the number then sign. Okay. Basically, number then sign means if the charge is like 2 positive. Okay. So you have to write first of all number, that what is the charge magnitude. So 2. Then you have to write the sign. So 2 negative. Okay. So, for the charged coordination entity, that charge, which is written in this manner, number and then sign. So, that charge is written as a superscript outside the brackets. When you, in the case of polyatomic ligands, when you like close the ligands in the parenthesis, then you have to put the superscript of the charge. Okay, you have to put the charge as a superscript of that bracket outside the bracket for the charged coordination entity. Okay, in the case of coordination sphere also, if our coordination sphere is anionic or cationic, then the charge is going to be present as a superscript outside the square bracket. Now, for example, we have cobalt Cn whole 6 whole 3 negative. So we have a charged coordination entity. The charge is 3 negative. Okay. So we write the 3 negative as a superscript outside of the square bracket, and also in the manner of number and then sign 3 negative. Similarly, the other example, chromium water molecules, 6 water molecules are bonding with the chromium and they are enclosed in square brackets having charge 3 positive, which is present as a superscript outside the square bracket. And in the same similar manner, number then sign 3 then positive. Superscript, okay, if you don't know, superscript is basically placed here at the top right side, and subscript you can place here at the like lower right side of the brackets. Okay. Seventh rule while writing the formula of the coordination compound is that the charge of the cations is balanced by the charge of the anions. So, in a neutral coordination compound or coordination compound formula, whatever will be the charge of cations, that are going to balanced by the charge of anions. Okay, so this is the seventh formula you have to keep in your mind while writing the formulas of the coordination entity. Let's move to the naming part, the section 5.3.2, naming of mononuclear coordination compounds. So, now let's see the rules for naming of any coordination compound. We have seen the formulas, rules for writing the formula. Now we see the naming formula. If you want to name the coordination compound, what will be the rules you have to keep in mind? So, coordination compound names are built using the additive nomenclature. Okay. Now, what is that? So, ligands are named first as prefixes before the central atom's name. Here, this is the opposite, right? From the writing the formula rule. Here, while writing the name of the coordination compound, you have to write the name of ligand first. Okay, you have to write the name of ligands first as prefix before the name of central atom's name. Numerical prefixes like dia, tria are used to indicate the number of each type of ligand which are present. If the ligand is more in number, if it is more than 2, more than 3, okay, then you can use the numerical prefixes like dia or tria to represent the number of the ligand that are present in our coordination compound. The following rules are used when you name the coordination compounds. Let's see. The first rule says that cation is named first. Okay, so we have cation and an ion. Two types of ion will be going to present in the coordination compound. Okay, the first rule says that you have to name the cation first, either square bracket part or the counter ion. Now, cation you have to name first, either it is present in the square bracket, either it is present like either it is a part of square bracket or not. Okay, or it is present as a counter ion. Counter ion means whatever the ion is present outside of the square bracket in the coordination complex, then that is considered as counter ion. So if our cation is present as a counter ion, or if it is the part of the square bracket, in both the cases you have to write the name of the cation first while writing the name of coordination compound. Second rule says that the ligands are named in an alphabetical order. Okay, alphabetical order means that if the ligands are so many, let's say two ligands are there or three ligands are there, you have to name them in alphabetical order before the name of central atom or ion. Okay, so before the naming of the central atom or ion, you have to name the ligands. And if there are more ligands or different type of ligand, then you have to arrange them in an alphabetical order or put them in the alphabetical order while naming of the coordination compound. This procedure is reversed from the writing of the formula, because remember we discussed that formula while writing of the compound, while writing the formula of the compound, that you have to name the central atom first, right? While writing of formula, remember. But while writing the name of the coordination compound, you have to write the name of ligand first before the name of the central atom or ion. Third rules is that names of the anionic ligands and in O, those of neutral and cationic ligands are the same. Now, ligands can also be of different types. So, if it is if the ligand is anionic, having negative charge, then its name while naming of the ligands, you have to end the ligand name with O. Okay, you have to just put a O at the ending of the ligand name. And if our ligand is neutral or cationic, then that ligand name is going to be same as it is. Whatever the ligand is called as, that you have to put in the naming of the coordination compound. There is some exception in this case, except aqua for water molecule. So if the ligand is water molecule, which is a neutral molecule, right? So you can't write it as water, okay, or aqueous. You have to write it aqua. So this exception. So these ligands have their particular name, like water has aqua. You can only use aqua for water molecule in the coordination compound naming. NH3 you can use amine, CO you can use carbonyl, and NO you can use nitrosyl. Okay, so these are the names for these four exception molecules that you can use while naming of the coordination compound. While writing the formula, these are enclosed in the brackets. Okay, now when you write the formula, these ligands are going to be enclosed in the brackets. Fourth rule is that prefixes like mono, dia, tria, they are used to indicate the number of individual ligands. Okay, so for every ligands you have to repeat this step, that you have to count the number of that ligand present in that coordination compound and then put the prefix like mono, dia or tria before the name of the ligand compound, before the name of the ligand. Okay, for every individual ligand you have to do this to indicate the number of that individual ligands which is present in the coordination compound. When the names of ligands include a numerical prefix, then bis, tris, or tetrakis terms are used. Now, what if the ligand name has already mono, dia, or tria name in it before you even put it while naming of coordination compound? Okay, so there are some cases where the ligands has mono, dia, or tria in their name already. Okay, then in that case, how can you show that that ligand is in two, or like there the number of ligand is 2 or 3 present in the coordination compound? Then when the names of ligands include already a numerical prefix like di or tri already in their name, then you have to use bis, tris, or tetrakis terms for like indicating the number of that those ligands. Okay, bis for 2, tris for 3, and tetrakis for 4. For example, NiCl2 PPH3 whole twice. Now this is a complex. This is a coordination sphere enclosed in the square bracket. This is named as diachlorido. Okay, because the chlorine is our ligand. Okay, here nickel is a central atom, chlorine is ligand, and this PPH3, which is triaphenyl phosphine, this is a ligand. Okay, now PPH3, this is a formula of the ligand. Okay, now whole twice determines that there are two number of triaphenyl phosphine that are present in our coordination compounds. Similarly, chlorine is a single atom, but two here in the subscript represent that two chlorine atoms are bonded with the central atom or ion, right? So here the central atom is nickel, the ligands are chlorine and triaphenyl phosphine. So you can name this complex as diachlorido, di for representing the two chlorine, and chlorido. Do, that means ending is with O. Why? Because this ligand is anionic. So diachlorido, bis, triaphenyl phosphine. Why we use bis? Bis is for two, for indicating the two molecules. And two molecules of triaphenyl phosphine is present. And the triaphenyl phosphine has already a numerical prefix in it, which is tri. So we can't write it like diatriaphenyl phosphine, right? So we are using, because already numerical prefix is present in this ligand, so we are using bis to represent the number of this ligand present in our coordination compound. And then comes the, after the ligand's name, then comes the central atom name, which is nickel here, and the and its oxidation number, which is +2 in the Roman numeral. So for this complex, we can name it like this. The fifth rule while naming of coordination compound is that oxidation state of metal, the central metal atom, is indicated by the Roman numeral in the parenthesis. Sixth rule, that if the complex ion is a cation, if we have that complex ion, that means that square bracket enclosed coordination entity, if that complex ion is a cation, the metal name, while you are naming that compound, the metal name is going to be same as the element. If nickel, nickel will be there. If the complex ion is cation, then the central metal name will be as it is going to be present in the coordination compound naming. For example, let's take the cobalt in a complex cation. So if the complex is cation, then the cobalt is the central metal, then you have to name it as it is, like cobalt, while naming of that coordination compound. Similarly, if the platinum is the central metal for any complex ion, which is a cation, then you write the name of platinum as it is, like platinum. What if the complex ion is an anion? If the complex ion is an anion, that means it is going to have negative charge. The name of metal, the name of central metal is going to end with the suffix 8. Okay. So while writing the anionic complex ion central metal name, you have to end the central metal name with 8 suffix. For example, if you take a complex anion COSCN whole 4 whole 2 negative. So this complex ion is an anion because 2 negative charge is present. So, and central atom is cobalt. So cobalt name will going to be cobaltate, not cobalt. It will end with 8 suffix. So cobaltate. Now for some metals, the Latin names are used in the complex anions. For example, ferret for iron. Okay. We call it as, Fes call it iron. But while naming it, we use a Latin name for iron, that is ferret. Name this like, or to name this metal. Okay. The seventh rule is that the neutral complex molecule is named similar to that of complex cation. Now, if the complex molecule have no charge, that means it will going to be neutral. That means while naming of that neutral complex molecule, the name of the central metal will be going to similar as the complex cation case. That means the name of the element will be going to be same. Let's see the example of nomenclature of coordination compounds. The following examples illustrate the nomenclature for coordination compounds. First example we are taking is chromium NH3 whole thrice. H2O whole thrice enclosed in the square bracket Cl3. So this is the complex we are taking for the nomenclature. Let's illustrate it. How you can name it? It is named as, first of all, the name of the cation will be there. Okay. So here there is no cation. Outside of the bracket only anion is present. So then we comes at the ligand name. Ligand name also in the alphabetical order. So triamine, triaqua, chromium third chloride. This is the name. So triamine, that means amine is going to be 3. So 3 molecules. So triamine. Triaqua, because 3 molecules of water is present and water is represented by aqua. So triaqua. You see AM and AQ. You remember the alphabetical order. So A is same in both amine and aqua. So we consider the second letter, that is M and Q. Q will go at the second place from the amine, like amine will come before the aqua, right? So triamine, triaqua. Now the central metal, chromium, in the oxidation state, +3 in the numeral, and then chloride. That is the counter ion or anion that is going to be present outside of the square bracket. So it is, this complex name is this. Now let's see the explanation. So the cationic complex ion is inside the square bracket. Now you can see that inside the square bracket, the cationic complex ion is present because this chlorine is going to have negative sign. Okay. And we have remembered that the cation will going to balance the charge of the anions. So if this anion, which is a chlorine, is having negative charge, the complex will be having a positive charge after the removal of chlorine from here, because only it can remove or it can dissociate, right? This complex ion or cationic complex ion will going to remain intact. The amine are named before the aqua ligands according to the alphabetical order, right? A is both, A is same in both. Then we consider the second letter M and Q. Q will come later than M. M will go before the Q. So that's why amine are named before the aqua ligand according to the alphabetical order. There are 3 chloride ions in the compound. Okay. So 3 chloride ions will was there. That means the charge on the complex ion must be +3, because 3 chloride ions will give us -3 charge. Each chlorine will have -1 charge. So when -3 charge will be removed, +3 charge will be go or will come at the complex ion, since the compound is electrically neutral. All ligands are neutral molecules here, right? Therefore, the oxidation number of chromium you can easily calculate, which will be +3. Why? Because it is going to be same as the charge of the complex ion, because every ligand is also neutral here. Okay. So the charge of the complex ion is +3, because 3 chloride ions are present as the counter ions. So when they remove having 3 negative, the complex ion will get +3 charge, and that is going to be same, or that is going to be same as the oxidation number of the central metal, that is chromium. Let's see the second example for the nomenclature. Cobalt, NH2CH2CH2 NH2 whole thrice, whole twice, SO4 whole thrice. Now how we do the nomenclature of this complex? So it is named as, its name will be tris ethane 1,2 diamine. Now here dia is coming already in the name of the ligand, so that's why we are using tris as a prefix to indicate the number of the ligand, and 3 ligand are present. So tris ethane 1,2 diamine, cobalt in the +3 state, and sulfate ion. Okay. So explanation is that the sulfate is the counter anion in this molecule, because sulfate is already present outside of the square bracket. So that is counter ion. Now it takes 3 sulfate to bond with the 2 complex cations, right? Because sulfate is whole thrice and complex is whole twice. So we take 3 sulfate to bond with the 2 complex cations. Why we are calling complex cation? Because sulfate is going to have 2 negative charge. So when it going to remove, it will going to give a positive charge to the complex. So 3 sulfate is going to be bonded with the 2 complex cation. So the charge on the each complex will be cation must be +3. Okay, so it takes 3 sulfates to bond with the 2 complex. Okay, that means the charge on each of the complex must be +3. Further, you can notice that ethane 1,2-diamine is a neutral molecule. So the oxidation number of cobalt in the complex ion must be equal to the charge of the complex ion, that is +3. Okay, from there the oxidation number comes for the cobalt. Okay, okay. Let's practice an example here. Example 5.2. Example is that write the formulas for the following coordination compounds. So we have given some 5 compounds. You have to write the formula for each of the following. A is tetramine aquachlorido cobalt 3 chloride. B potassium tetrahydroxido zincate +2. C is potassium trioxalato aluminate +3. D is dichlorido bis ethane 1,2-diamine cobalt +3. And last E is tetracarbonyl nickel 0. So all these things which are present in Roman numeral are basically the representation of oxidation state of the central atom or ion present in the coordination compound. You have to give the formula of these names of the coordination compound. So you have given some time, try to solve this, analyze this, and then we will see the correct answer and correct solution. Okay, let's see. So for this given question, so for this example, we use the rules for writing the formula that we have seen, right, for each part. Let's begin with the first part, that is tetraamine aquachlorido cobalt +3 chloride. The formula will be for this will be cobalt NH3 whole 4 H2O chlorine enclosed in the square bracket and then Cl2. Let's see step by step. So central metal here is cobalt, because we have seen that the oxidation state, that is +3, is given in the Roman numeral with the cobalt. So cobalt is going to be our central metal. Now the oxidation state you have to identify for the cobalt, that is +3, already given in the name, +3 in the Roman numeral. Now the ligands comes within the square bracket. So ligands are the ammonia molecule and the water molecule. From the name you have to identify. So tetraamine aquachlorido. So amine, aqua and chlorido, 3 molecules are present. So ligands will be tetramine, that is NH3 molecule, and there is 4 number of molecules of amine because tetra prefix is using. So amine molecule is basically neutral. Then comes aqua. Aqua is for water molecule we are using here in the name. So aqua is 1 molecule because there is no prefix we are using here before the aqua, right? So only 1 molecule is present for the water, and this is also a neutral molecule. Chlorido, we have given chlorido. Remember, we have said that we will end the name of the ligand with O if the ligand is an anionic. That means there is chlorine present as a ligand and 1 ion is there because no prefix is using for indicating the number of this ligand, and also the charge it would carry will be -1. Now if you calculate the coordination sphere charge calculation, coordination sphere charge calculation will be the sum of every coordination entity charge. Okay, So plus 3 charge will come from the cobalt because it's the charge it is carrying, the oxidation state it is carrying in the coordination compound. So plus 3 from the cobalt plus 4 times 0 from ammonia molecule, because ammonia is a neutral molecule, it will carry the 0 charge. It will contribute 0 charge to the sphere charge, and 4 number of molecule of ammonium is present, so 4 times 0 plus 1 times 0 from water molecule. Again the similar concept, one molecule of water is present, aqua molecule only one is present, and it is a neutral, so it will give, or it will have 0 charge. So 1 times 0 from water plus 1 times minus 1 from chloride ion, because only one chloride ion is present, and it is also carrying minus 1 charge. So 1 times minus 1 from the chloride ion. Now when you sum this, plus 3 from cobalt and minus 1 from chloride ion will contribute to 3 minus 1, that means plus 2. So the coordination sphere charge is going to be plus 2. So the complex ion is cobalt NH3 whole 4 H2O chlorine whole plus 2, or 2 plus. Okay, we write the number first, 2 plus. Okay, so cobalt is our central atom, ammonia, water molecule and chlorine, they are ligands with their specific numbers as given in the name, and the charge we have calculate for the sphere, that is 2 plus. Now we visualize the counter ions if there is any outside the square bracket present. So there are chloride, because after the naming of the coordination compound we have mentioned here chloride, which is going to be the anion, right? So chloride, that is Cl2, two ions will be going to present. Why two ions is going to present? Because each one carry the minus 1 charge, that means total charge will going to be minus 2, that is going to balance the plus 2 charge of the complex ion. Remember, we have seen that while writing the formula, we have to keep in mind that the cation and the anion should balance each other. So we have cationic complex having charge plus 2. So the counter ion will going to be having charge minus 2. So chlorine atom will going to be, or chlorine ions, chloride ions will going to be present as a counter ion in the two numbers. Two ions will be present, each carrying minus 1 charge to balance the plus 2 charge of the complex ion. So, and coordination number if you calculate, it is going to be 6. Why? 4 from the ammonia, like 4 ammonia molecules are bonding with cobalt, 1 water molecule and 1 chlorine molecule, chlorine atom or chlorine ion. So 4 plus 1 plus 1, that is 6. So coordination number will be 6. Okay. So we had determined the formula for the tetraamine aqua chlorido cobalt third chloride, that is cobalt NH3 whole 4 H2O chlorine, and counter ion will be Cl2. So let's see the next part, which is potassium tetrahydroxido zincate plus 2. The formula for this will be K2 zinc OH whole 4. How? So simply the similar steps. The central atom, the central metal you have to identify. Here the central metal is zinc, because with the zinc we have the Roman numeral oxidation number. So central metal is going to be zinc. The oxidation state of zinc will be plus 2. It is given in the name. Then ligands within the square bracket, they are tetrahydroxido. Hydroxido means hydroxide ion. Okay. So tetrahydroxide ion, that means 4 molecules of hydroxide ion is present, each carrying negative charge, minus 1 charge. This potassium is a cation, and we have remembered the rule that cation name is going to be first, like while writing the formula. So potassium is representing the cation, so it is not going to be the ligand. The hydroxido with the prefix tetra is indicating the number of hydroxide ions present as a ligand in the molecule. So 4 molecule of hydroxide is present, each carrying negative charge. Now coordination sphere charge calculation you have to do. So plus 2 charge will come from the zinc because it is having plus 2 oxidation state, plus 4 times minus 1 charge is coming from the OH, that is hydroxide ligand, because they are 4 in number and each carrying minus 1 charge. When you add it, plus 2 minus 4 will become minus 2. That means the coordination complex ion is going to be zinc OH whole 4 carrying the charge 2 negative. Now the counter ions you have to see if there is any. So outside the square bracket there should be the counter ion. So there is the potassium, and potassium, two ions will going to be present because each one carry +1 charge. So two ions is going to balance the -2 charge of the complex ion, because 1 plus 1 will become 2. That means +2 charge of the cations of the counter ions will going to balance the anionic complex ion carrying the charge -2. So coordination number, if you calculate, it is going to be the sum of ligands. So 4 number of hydroxyl is arranged around the central atom zinc. So it will be going to be 4. Okay. So the formula will be zinc OH whole 4 square bracket, and the K2 is present as cation. So K2 zinc OH whole 4. Let's see the third part, which is potassium trioxylato aluminate third. The formula for this will be K3 aluminium C2O4 whole thrice. Now, similar step, the central metal you have to identify. Here the central metal is aluminium, because with the aluminium the oxidation state is given. Now oxidation state of aluminium is +3, already given in the name. Now ligands which is present inside the square bracket, that are going to be trioxylato, that means oxalate. Also the trioxylate, that means oxalate in the 3 number. So 3 molecules of oxalate will going to be there, each carrying a charge -2. Now the coordination sphere charge calculation, 1 plus 1 times +3 from aluminium. So +3 will come from the aluminium, that is central atom, because of its oxidation state. Plus 3 times -2 from the oxalate ligand. Okay. So because each we have 3 number of oxalate ligand and each carrying -2 charge, so 3 times -2. When you add it, +3 -6 will be -3. So coordination complex ion is going to be aluminium, the central metal, C2O4 whole thrice, whole 3 negative. The counter ions that are going to be present outside of the bracket will be potassium, because already present in the name potassium. Okay, name is starting from potassium. So cations is going to be present outside the square bracket as a counter ion, and they are also in the 3 number. 3 ions of potassium is going to be there, each carrying +1 charge, so that 1 plus 1 plus 1 will +3, and +3 charge is going to balance. +3 charge from the cations is going to balance the anionic charge of the complex, that is -3. And if you talk about the coordination number, it will be the sum of biadentate ligand. So we have oxalate. Oxalate is a biadentate ligand. That means it can bind through 2 donor atoms at the same time with the central metal. Okay. So it contains 2 donor atoms basically to bind with the central metal. That's why its density will be 2. And 3 molecules of oxalate is present. So 3 times 2 will be the coordination number. That means 6. So formula will be potassium, that is K3, 3 number of potassium, then aluminium C2O4 whole thrice. Let's see the D part, that is diachlorido bis ethane 1,2-diamine cobalt 3, whose formula will be cobalt Cl2 En whole twice positive. Now the similar steps, the central metal you have to identify. Here it will be cobalt. Then you have to identify the oxidation state, which is +3, already given in the name. Then you have to see the ligands which is present inside the square bracket. So here in the name diachlorido, so chlorine should be the ligand. Bis ethane 1,2-diamine. Ethane 1,2-diamine is a ligand, and bis is present, which is indicating 2 number of ligands of ethane 1,2-diamine. So 2 En will going to be present as ligand. So ligands are first of all chloride, which is 2 molecules. So charge each will carry -1 charge. And then the bis ethane 1,2-diamine, that is En whole twice, that means 2 molecules, and each molecule is neutral. Now the coordination sphere charge calculation. So +3 will come from cobalt, 2 times -1 comes from the chlorine. Okay, because 2 chlorine are present, each carrying -1 charge, so 2 times -1, plus neutral molecule is En is neutral molecule, so 2 times 0 from the En whole twice. When you add them, so plus 3 minus 2 will be plus 1. The charge is coming out as plus 1 for the complex coordination sphere. So complex ion will be cobalt, the central metal atom, then chlorine in the 2 number, and then En, the ethane 1,2-diamine ligand in the 2 molecule of it, carrying the whole charge as plus 1 of the complex ion. Then the coordination number you want to write out, it is going to be 6, the sum of ligands. So 2 will going to be from the chlorine, and 2 times 2 will going to be the from En. En is a diadentate ligand, so it is going to have 2 denticity, and 2 number of En is present, so 2 times 2. Okay, so 2 times 2 is 4, 4 plus 2 is 6, so coordination number will be 6. And there is not the presence of any counter ion outside of the square bracket. How we identify that? Because we haven't mentioned any anion at the end of the name or the cation at the initial of the name. That means our the complex is going to be our ion in the ionic form. Okay, and that's so in the cationic. Now let's solve for the E part, that is tetracarbonyl nickel 0, that is NiCO whole 4. Again the same thing, central metal you have to identify. Here it is nickel. Now oxidation state of nickel is 0, already given in the name. When you find the ligands within the square bracket, it is going to be tetracarbonyl. Okay, already given in the name, tetracarbonyl. So tetracarbonyl, that is CO carbonyl, having 4 molecules of carbonyl present as a ligand in this compound. And so each ligand or each molecule is neutral. So coordination sphere charge calculation will be 4 times 0 from the carbonyl and 0 from the nickel. Nickel have 0 oxidation state. So the coordination charge sphere calculation will be 0. That means charge is coming out as 0 on the complex ion. So the complex ion will be NiCO whole 4. That means no charge is going to be present. This is a neutral coordination compound. So formula is going to be NiCO whole 4 for the tetracarbonyl nickel 0. And coordination compound, coordination number, which is determined by the bonded ligands. There are 4 number of carbonyl as a ligand present in it. So sum of ligands will be 4 times 1, that is 4. So coordination number of the central atom nickel will be 4. Okay. Okay. Let's see the summary. The part that we have covered today from the section 5.3. So first of all, the IUPAC, which sets the standard for naming of the coordination compounds. Central atom is listed first while writing the formula. This we have seen that while writing the formula, you have to write the central atom first. Then the ligands are then listed in the alphabetical order. After writing the name of the central atom, you have to write the ligands in the alphabetical order. Formula for the entire coordination entities is enclosed in the square brackets. The charge of the cations is going to balance the charge of anions. The ligands are named in an alphabetical order before the name of the central atom or ion. Okay, so ligands are named in an alphabetical order before the name of central atom while naming of coordination compounds. Anionic ligand, if we have, they end with the O if they are anion. Okay, the ligands, if they are anion, then their name will end with O. If they are neutral or cation, then the ligand's name will be as it is. Their name will be same. We use some exception here. Some exception here is that we use aqua for water molecule as a ligand, amine for amine molecule as a ligand, carbonyl for carbonyl molecule as a ligand, and nitrosyl for NO molecule as a ligand. Prefixes like mono, dia, or tria are used to indicate the number of individual ligands present in our coordination compounds. Oxidation state of the metals is indicated by the Roman numeral. cation complex has the metal name same as the element. If the complex of like our compound is cationic, then the name of the metal is going to be same while naming. If the complex is anionic, then the name of the metal end with a suffix ate, like cobalt will written as cobaltate. Okay. Neutral complex will be there if there is no charge in the on the complex ion on the complex molecule. Then the molecule name will going to be similar to that of the case of the cation. That means it will the element name is going to be same as the name of the element. Okay, while naming of that coordination compound. Okay, thank you. So this is all for today's chemistry session. Thank you so much.